Hello, everybody. We had a midterm 3 in the last lecture. I haven't yet graded them. Most probably during the weekend. That's when you can expect it to be graded. Surely by the end of the weekend. That's when you want to look for it. The solutions were out right after the exam itself, so you should be able to at least have a feel for how you did, but the actual grading will take a little bit more time. That is basically by the end of weekend. About how things go from this point on, let me zoom this in. Right. We have, I have posted a homework 8. This is due November 5th. That's a Thursday. Remember that there is no class on Tuesday, so November 3 is a holiday. Tuesday. But you should be able to do homework 8 based on the past lecture. So lecture, it's all based on lecture on 22nd. So you should be able to do it right away. There will be homework 9. Homework 9 has been split into 2 because chapter 9 has significantly important stuff. So I'll be covering this in 2 weeks. And this is due November 10th. Notice this is right the Tuesday following the Thursday next week. So, but still we will have 2 lectures, whatever we do today and on Thursday, that's what will be covered there. So the lectures on lecture based on lecture on today. So that's October 29 and November 5. This has not been uploaded yet. Will be uploaded very soon. So by end of today, probably will be uploaded. So that's the homeworks. There will be 2 more homeworks by the end of the semester. There will be homework 9, which is just for your information. That will be on November 17th. And there will be a homework 10 that will be due December 3rd, I think. These are tentative, so at this point, I think we don't have to do that. Before homework 10, actually, that is midterm 4. The lecture before, the last lecture before Thanksgiving, so that's November 19th. So that's a tentative plan. Final exam. It's visible. Oh, I should pin it so that I am able to see it. Yeah, final exam is December 10, Thursday. So that's some of the information that's relevant. Okay, so we want to discuss what we started last time. We talked about rotational kinematics. We want to discuss how things rotate about an axis. And the motivation was, remember, any rigid body, by rigid body we mean points inside of the body do not move with respect to each other. The whole body is moving. And rigid bodies, when you throw it around, they can be broken into two kinds of motion. One is the motion of the center of mass, and the second is a rotation about an axis going through the center of mass. And what we are talking about today and in the next 2 weeks is this rotational motion about an axis passing through the center of mass. So this is a rotational motion. This should be compared with translation motion. What we said is that there is time, the same as, let me say translation motion here just for comparison. Translation.
Can you zoom in? It's a little hard to see.
Oh, that is hard to see. And why is that? Let me zoom in, maybe. Is this any better?
Yeah, that's better. Thank you.
Should I zoom more? I think actually this is the maximum. Okay, so let me set this. Okay. When I go to the other side, I'll set it in. Okay, so I'll also try to write figure. So this is translation motion. Rotational motion, translation motion. Translation motion as with things going in a straight line. This is things going in a circle about an axis. Both have time involved. That's the same. There is no difference in the concept of time associated with rotational or translation. We have in rotational motion, change in position is change in angles, right? So this is displacement, angular displacement. And here we set simply delta x. And if there is a connection between that, especially when a wheel is rolling, there's a connection between them. So conceptually, it is good to remember that these two are related by delta x is equal to r times delta theta. So you multiply, or maybe I should write it on the other side, right? It doesn't matter. The translation displacement or the linear displacement is related to the angular displacement by a radius vector. And this radius is basically the distance of the point which is moving with respect to the axis. The diagram helps. This is your rigid body. Let's say that's your axis. So there is some point here on the rigid body. It moves. So that's your angle delta theta. That's your delta x if you want, if you spread it out on that. And this is radius r. It is r times delta theta is equal to delta x. That's delta x. Hopefully it's readable. Then we defined what is angular velocity. Angular velocity was change in the angular displacement over the change in time. And here there was a similar concept. Velocity is change in displacement over change in linear displacement over change in time. And if you were to do that here, there is a relation again. V is equal to omega r. Like this, omega r. again, notice the distance from the axis coming into picture, which we say the radius. If it was just a simple mass going around, so that you just say it is the radius. Acceleration, that's angular acceleration. That's change in angular velocity over time. Here it is change in velocity over time. And again, these two are related. This acceleration is equal to alpha times the radius, or translational acceleration is equal to the angular acceleration times this radius r. So that's where we were. We talked about kinematics related to the rotational motion, very much like the kinematics associated with the translation motion. But then what did we do here? There was a leap we made. That's what Newton provided us with that. The first thing was we talked about two concepts, right? There was mass, so which is often better in this context to talk about it as inertia. This is mass, but let's interpret it as inertia. In what sense is it inertia? It has to do with, so if you are providing a force, for the same force, the acceleration will be inversely proportional to the mass. That means more mass means less tendency for it to move. So the mass makes sure that acceleration, or the mass doesn't like to move if there is a force provided to it, and that is decided by how big the mass is. If you're very heavy, the tendency for you to move is less. So that's the idea of inertia. And we also pretty much parallelly both came together, right? So this is force. And the Newton's law is F is equal to ma. Better if there are many forces acting, so it is ma is equal to F1 plus F2 plus so on. And it is a vector equation. So that was what, and all this came together. Like we best is to go to this equation and say that if you were to divide this by mass, acceleration is inversely proportional to mass, or another way to say it is that what is resisting the acceleration? Given the same amount of force, what other factors actually decide what the acceleration will be? And it turns out to be the mass in this case. We notice that if it is more massive, less tendency for it to move. And we want to ask the same thing here. What is the associated concept here? What is the rotational inertia? So we want to talk about what is rotational inertia. What is the rotational force, which will be called the torque? So this will be, so maybe I should, so this will be called moment of inertia. Rotational inertia will be called moment of inertia, and rotational force will be called torque. And there will be a connection between the two exactly the same way as this. Let me give it some names. So this is I. This is moment of inertia. That's the analog of mass. So that's the analog of mass. We'll find the relation here. And the torque will be a tau. So that's not T, that's tau. So this is tau.
Can you move it down so we can see that?
Other again?
Can you move it down just a little so we can see it all?
Okay. 4 and 4. Okay. It was visible on my screen. That's weird. Okay, that's okay. Just let me know whenever you want me to move things around. Okay, so that's tau. So that's your rotational force. And there will be a connection between these two also. And the relation, the Newton's law for the torque will be just mass of I times alpha. Notice I is mass, alpha is acceleration, is equal to this time torques. And they will be vectors, but we will see that there will be a simplicity in this course. So that's pretty much the summary of what we are going to do in the next two lectures. We want to introduce the torque today, which is the corresponding idea of force, and the moment of inertia we will do in the next lecture, and then we will talk about the angular Newton's law and how to do applications with them. So let's think about the idea of torque. Okay, so move the camera and I need to zoom it, I guess. Okay. Here. So what is torque, right? We want to talk about what is torque. So torque is, think of this as angular force, or actually the technical word is moment of force. Okay. So let's think of a practical situation. And so this is a door. And in what sense is this a door? This is actually able to move this way. This door opens and closes in this direction. That means if I were to, so we are looking at, so this is the axis of the door. So this is the axis or the hinge, right? Axis of the door. So I think this can move around this way, and this is a cross section we are seeing. So it is a very thin bar we are seeing. Actually, it is a whole plank, right? There is a slab of wood there, but we are seeing through from the top side. So we are only seeing the thin cross section of the door. And we would like to move this door. And it is free to move to the left or about the axis. It can actually go counterclockwise or clockwise. Remember, whenever the axis is coming out of the board, there is two directions. Counterclockwise is positive and clockwise is negative. So that's your door, and let's exert a force. So we exert a force on this. At the very end, and we would like to know how does it move. And the angular force will be defined as, this is the torque, will be defined as how far you're from the axis. So this distance comes into picture. So this is, let's say, how far you're from the axis. So that's your L. So that is the length of the door, let's say, in general. So this is R. In this case, R is L times the force itself times the angle between the force and the distance. Right? So what do I mean by that? So what I mean is, from the axis, this is a distance vector of length L, and the force is in this direction. That's your X. And it is the angle between them. In what sense is the angle between them projected either you move the force here, keep the tail end of the two vectors same, or just find out what is the angle. If you were to project this line forward, this is the angle between them, and that's 90 degrees. So that's your theta. And you notice that the torque is actually equal to L times the force F. And why do we do that? Because we know that if I were to, instead of exerting the force perpendicular to the door, what if I were to exert the force in this direction? Like opening a door could be a skill, right? When we were very young, very almost kids, it might not have been obvious as to how, in what direction should we push the door to open the door in a very efficient manner. And for that, suppose one of us were actually to pull the door in along the direction of the axis. So there is an axis and there is a door, and if you were to pull it along the line in which the door is, then we know that it's not going to open, right? You're going to be pulling it along the axis, nothing is going to happen. And that should somehow get represented in the force, and that's why we have this angle coming in. So now let's do this again for the new scenario. So new scenario is that you have, this is the direction, again L, that's a displacement, or not really displacement, this is a distance at which the force is acting, and the force itself is in this direction. Both are in the same direction, and the angle between them then is 0. So the torque is equal to L times F times sine of 0 now. Earlier it was sine of 90 degrees, that's 1. In this case, now it is sine of 0. Sine of 0, unlike cosine of 0, is 0 when it is actually the angle 0. So that's equal to 0. So that seems to convey the point that yes, indeed, if you were to actually pull it along the line in which the axis and the point of contact is, then it is actually 0. And that's why we want to bring in this angle. Just the force alone will not capture that, because if force alone was causing angular motion, both of this should have done the same job, but it doesn't. There seems to be also a distance here. What is the role of that? We know that if you were to come closer, everyone can ask, why do we have the door handles on the very edge of the door? Why not keep the door handle somewhere in the middle? That's because it's not very efficient, or you need to put in more force actually to push the door and open it if the hinge was closer. So it just makes it more efficient. So how do we see that? See, again, we do the same exercise. So this is now L over 2. And the force is again perpendicular. And you can project this forward, and this is 90 degrees. And you would say the torque is equal to L over 2 times the force F times sine of 90 degrees. Sine of 90 is 1. So it is L times F over 2. L times F was the torque you obtained when you exerted the force on the very end of the door. And this time there is only half of the torque that is available. So we want to define the angular force in this manner so that we can capture the fact that it depends on the distance from the axis of where you're exerting the force, and also in what direction you're exerting the force. For that matter, even if whether you were exerting it in this direction, like one could ask, if you were to exert in this direction or in this direction, right? Which one would be more? So let me give that as an extra credit problem. So let's say here, right? Extra credit. So discuss two situations. So that is a door. In the first case, you exert a force making an angle of 30 degrees, or let's say 45 degrees with respect to the x-axis. So that's case 1. And in case 2, you do the same scenario, but this time you exert the force in the inward direction, but at the same 45-degree angle. Okay. You want to use this torque formula and find out which one will cause more torque. And more torque means more angular motion. We haven't reached there yet. We are going to tell that we are going to connect this torque with the angular acceleration. So the question is, which of these two situations causes more angular motion? Okay, so that's all good. So it seems like we have introduced the idea of a torque here. Let's make this a little more formal. Maybe this can be all combined together as a vector equation. Torque, after all, seems to be defined as a vector. So let's very quickly review what is called a vector cross product. And I need to zoom in again. Okay. So we want to define what is called vector product, or either you say it is vector product or a cross product of vectors. Earlier we have talked about scalar product. That means if you multiply two vectors, you get a scalar. But now if we want to define a product where you multiply two vectors and you get a vector out of it. So let's say there are two vectors and we want to multiply it to get a third vector. So this will be the third vector, and this multiplication will be represented by cross. This is the multiplication sign. So A times B, often you say A cross B. Right? C is equal to A cross B. How do we define this? So let's say the vector A is equal to, write it here so that I can get some space. So vector A is equal to AX in the I direction plus AY in the J direction plus AZ in the K direction. But most of the time here we will be talking about vectors which are in a plane, but let me define it as a general vector anyway. This is AZ in the K direction. That's the three components of the vector A. Vector B similarly is Bx I direction plus By in the J direction plus Bz in the K direction. And we would like to define what is the vector product of these two vectors. The procedure will be to write this. This is just a mnemonic to get this product memorized. So write ijk's in a row. Write the components of vector A in the second row. And write the components of vector B in the third row. And this two lines here has a meaning. It's called a determinant, but that's just a procedure, so which I'm going to define for you. Okay. So how do you define this? So this is going to be equal to, I'll say I want to write down the component in the direction of I. Notice when I fix my I can remove the row elements in there and remove the column elements that contains the I. once I remove that, there are 4 elements remaining in that, and write those 4 elements down. So this is AY, AZ, BY, BZ. Just a procedure, it's a prescription. It's like defining the product, right? 3 times 2 is, this has deeper meaning in it, but as far as we are concerned, we are just use at a user level. This is how you use it. The next one is J, but then I have to swap the sign, alternate the sign. So first one is positive, the next one is negative. Again, do the same thing. Remove the row that contains J and remove the column that contains J. And what is remaining is AX, AZ, BX, BZ. And finally, K, do the same thing. Remove the row and column containing K, and you have AX, AY, BX, BY. Okay. Then you define, maybe write a little bit on the left. So this is equal to the component in the I hat direction is going to be, I multiply these 2 vectors and then subtract the product of the other diagonal. So notice first I go down, that's AY times BZ. And then I subtract out the other product. There are 2 diagonals I can construct. So this is BY or AZ times BY, right? That's better way of writing. So this is AZ times BY. It is again, I start from, look for the diagonal, multiply the 2 main diagonal, and the off diagonal elements I again multiply and then subtract them out. Do the same thing for other 2, that's AX, BZ minus AZ, BX, and plus K hat times AX, BY minus AY. That's the explicit definition of a vector product in terms of components. Most of the time, when we are working on this, we will be working in scenarios when A and B are in the plane. So these 2 components are 0. AZ is 0 and BZ is 0. That means if A and B are in the XY plane, we have AZ equal to 0 and BZ equal to 0. So wherever we see AZ or BZ, we can put it to 0. This product goes away, that goes away, that goes away, that goes away. Almost everything went away except the K component. So A cross B, so C equal to A cross B. Both A and B are in the plane XY, but the cross product, the C is in the direction of K. Like in the direction of Z, it is either coming out of the board or going into the board. That's AX BY minus AY BX. Significantly simpler. And this is in terms of the components. If we want to write it as a magnitude, so this will be let me just say magnitude of C will be equal to magnitude of A times magnitude of B times the angle between them, or times the sine of the angle between them. So this angle theta is the angle between A and B. So if I were to have 2 vectors A and B, That's this angle theta in there. And its direction is in the z direction if A and B are in the x and xy plane. In general, this is given by the right hand rule. So if you want the direction of z, maybe I should move this. So C is equal to A cross B. That's a vector product. Its magnitude is, when I don't write the vector sign, that means it is a magnitude. That's equal to A times B times sine theta. The torque definition seems to come in the picture there, sine theta, force, and distance. But as of now, it is just a general definition of cross product. What about direction? In general, what is the direction? So in general, how do you find the direction is what is called the right hand rule. It's necessary, as the rule has in it the right hand. So let's say this is your vector A and that's your vector B. It's not necessarily in the plane of the board, but in general, given any two vectors, it is possible to put it in the plane of the board. So what is the right hand rule? So you have to use the right hand. It is important that you use the right hand. Usually when you're writing, most of us are using the right hand, then it is tempting to use your left hand. No, that's not wrong. You will get wrong results if you use your left hand. So you have to use your right hand. So begin by having your thumb closed. So don't hide your thumb and point all the four fingers in the direction of A. Point all the four fingers in the direction of A. And then you will notice that there is a freedom to rotate about A. Right? I could actually face my palm in any direction I want to. So first thing is to point in the direction of A with the freedom to rotate your hand if you want. Then you rotate your hand in such a way that the palm, so the palm is facing B. Your palm should be facing B, and in that stage, you open your thumb, and the thumb represents your direction of C. So the rule is A is the fingers, all the four fingers, and then you rotate your hand in such a way that your palm faces B, or palm is pointing in the direction of B. Again, this is my A. I have this freedom, but I fix it. So I do not allow my, I get rid of the freedom by pointing the palm in the direction of B. This palm has a direction that's facing the vector B. And in that state, I open my thumb, and the thumb gives me the direction of C. The C is the thumb. If I were doing B cross A, I would do this, right? I can rotate around. I start with B, and then I have a face in the direction of A. So the palm has to face A, and then I open my thumb. It is going into the page. So A cross B is not the same as B cross A. In fact, it is going into the board. And if your A and B vectors are in a plane, which is what we would do, there are only two possibilities. Either it is coming out of the board or it is going into the board. Out of the board will be positive and going into the board will be negative. That depends on your axis, and one will be clockwise and one will be counterclockwise. In most of the cases that we deal with, it will be easy in the sense it will be either clockwise or counterclockwise, and it will be much more easier to just look at it as an intuitive feel for what the force is doing. You don't have to explicitly use right hand rule, but it is good to know this in case you are ever in a doubt. It is easy to use this. This is much more formal. It will always work, but most of the times, especially in this course, you will be able to work with intuition and still do most of what is needed. So that's your vector product. So why did we introduce this? Because we wanted to introduce the idea of torque in terms of vector cross product. So formal definition of torque. Torque is a vector. This is equal to R crossed with the force. F is the force here, obvious, but R here is the distance of the point at which the force is acting from the axis. Always there is an axis, correct? Rotation is always discussed in terms of the axis. Its magnitude is R times F, that's R times F times sine theta, where theta is the angle between them. So for example, if this is your R vector, and if that's your force F, it's the angle between them. Notice you want to bring the tails together or else project it outward, and that's the angle between them. It is not this angle. It turns out that either if you use either one, it is okay, because sine of 180 minus theta is always sine of theta. So you don't do any error even if you were to actually take this angle. But technically it is the angle between the vectors, so it is this angle that is relevant. So the magnitude of the torque is R times F sine theta. And if they are in a plane, this is either positive or negative, right? It is, if it is, for example, this force, and if it is, this is your axis, this is going to try to move it counterclockwise. Just intuitively, we know that if I were to push something in this direction, it will actually go in the counterclockwise direction, and that's positive. Right? So that will be a positive torque. And if the force were exerted in the downward direction, it will be actually a negative torque. And as we proceed and do examples, it will be clear how you want to use this. So that's the definition of torque. So let's do some examples. The example is, let's consider a plank. So this is a simple a platform, if you want, a thin platform, a seesaw, like think of a seesaw, right, where you sit on two sides and one of them goes down, one of them comes up. So that's a in most of the children's park you see that. And this is a uniform rod, if you want, or a uniform strip of wood. And it's, since it is uniform, its weight, this is your center of mass, right? So this is center of mass. What that means is that the weight of this plank acts on that point. That means to say this is your mg, acts there. But before that, let me, I'll digress a little, but before that I should draw the seesaw. The seesaw is slightly tilted in the sense that its fulcrum is free to move around this point. So that's just a point where this can go up or down, right? This can go this way or that way, either way. So this is your axis. That's the axis. Let me mark that. That's your axis. And we would like to know how much this moves this way or that way. And to begin with, let us say there is a mass M1 that's sitting on the extreme right side of the plank. And that could be a kid. And let us say M1 is equal to 40 kgs. That's a 30 kgs. Two significant digits. We would like to balance this, but before that, there is a plank here. So the plank, where does the mass act? So before that, M1G, what is the forces acting on this? That is M1G acting downward. So this is your ground. M1G is acting downward. This platform also will be pulled down, so that since it is not at the center, that's your capital MG. Capital M is the mass of the platform. Let's say that's equal to let's say 10 kgs. That's a very light plastic, made out of plastic. Let's say relatively light. Like that's 10 kg, and that is a relatively heavier guy sitting onto the left, and let's say that's 2. But I'm not saying that it is to the extreme left. We would like to find out how far should he or her should be sitting so that it actually balances out. So that's your M2. Again, to clarify, so let me draw this again. So there is an axis here. That's the center of the plank. That's the forces acting. So that's your mg. Remove the clutter from there. That's your m1g. So kid, and the adult could be somewhere here. So that's your m2g. The system consists of M1, M2, and the plank, and we would like to know what are the other forces acting on it. Obviously, this cannot be completely correct because all three are acting down. There has to be a force that's upward, and that is coming from the axis itself. Right at the axis, this fulcrum will push it up, right? So there will be a normal force here. That's where the contact is happening. So that is the only place where the contact happens. So that's the normal force in there. And what we want to ask is, if this was L, let us say this is length L, that's your length L, and that's your distance D. How far should this X be? So let's say L is, it could be half a meter, right? So it could be 0.50 meters. D could be slightly shifted off. So that's 10 centimeters shifted off, let's say. That's 10 meters. So this is 50 centimeters. That's relatively small. Two significant digits. And we would like to know what is X. And I have to give you the mass M2 also. M2, let us say, is an adults, so that's 70 or 80 kgs. Hopefully it is long enough that it balances out. Is to find where should this M2, the heavier mass, be placed so that this doesn't move, right? This is actually balanced, and many of us have done this, and it is very easy to realize that if you're heavier, you ought to be closer so that the torque is less. Torque is more if you're farther away. That is why when you open, when you're using a wrench, then you're actually having a long handle on it that actually helps you to give more rotational force on it. Rotational force is the torque. So if you want to give more torque to it, you want to have a long arm. That's the way to say it. So here, since this is heavier, you want to be closer. So that's the idea. So, but let's analyze this using the torques, right? So the goal will be the torque due to 1 plus torque due to 2 plus the torque due to the capital mass, which is the Planck, and the torque due to the normal force all have to balance, right? If they don't have to move, right? So there are 4 torques. So torque total is equal to torque. Since the axis is fixed, there is only 2 possibilities, right? Either the torque is in the clockwise or negative, or in the counterclockwise direction. So I don't have to actually use the vector form. I can say either it is positive or negative. And most of what we will discuss will be in that form. So torque can, the vector nature of the torque doesn't have to be explicitly written. So you don't have to show that in the problems we are discussing. In general, you have to. So that's, there are 4 torques, torque 1 plus torque 2 plus, I might go off the board, so I should start a little from the left. So total torque is torque 1 plus torque 2. That's the torque due to the gravitational force M1, torque 2, gravitational force M2, and that is a torque due to capital M, and that is a torque due to the normal force. And they all have to be equal to 0. That's our goal. So let's begin by calculating the torque due to the normal force. Torque due to the normal force is distance from the axis, right, times the force, which is the normal force, times the angle between the force and the distance. But the distance is 0. The normal force is acting right on the axis. This is equal to 0. So that's equal to 0 immediately. So the torque due to the normal force is 0. So what is torque due to the mass 1? The torque due to mass 1, again, R times M1G this time, times the angle between these 2 quantities. So let's analyze this. So M1, if you see from the axis, this distance is L plus D, so that's 0.60 meters, right? So the distance of M1 from the axis is L plus D, so that's 0.6, so that's 0.5 plus 0.1, so that's 0.6, and M1G is acting downward. Oops, almost from the edge. And this is angle between them is 90 degrees. So you would say this is 0.60 meters. M1 is 30 kg times 9.8 times sine of 90 is 1. And now I have to worry about the sign here. Notice this force, you can almost look at it and say that when I push something here, this will tend to move it in the clockwise direction, right? Which is negative. Clockwise is always negative. So I put in a sign here, which is negative. Right? To begin with, I say that's negative. Why did I put the negative? Because this tends to move it in the in the clockwise direction. Again, keep the axis and imagine you're opening a door this way. Is this moving clockwise or counterclockwise? Counterclockwise is positive, clockwise is negative. So I introduce the negative sign in there, and that's minus of how much? So 6 into 3, 18 into 9.8, right? So that's 176. That's two significant digits. It's 180. And what's the unit of torque? There is a force and a distance. So it's just simply Newton meter. Right? There is no special unit for torque. You just say it is Newton times meter. That's your torque 1. And let me write that here and use the space again. So that I can erase. Oops, that went off the board. That doesn't help. Okay, let it stay as it is there. And torque 2 now, similarly, is on the other side. So let's again, now let's, before we begin, let's ask, is it going to move it in the clockwise direction or the counterclockwise? That's the axis. When I'm exerting a force, the tendency of motion for this is to go in the counterclockwise direction, right? It is moving in, it is going to make it go this way. That's actually counterclockwise. So immediately you say that's positive. How far is it from the axis? That's x. That's what I want to find out. That's what we want to find, that x. And what's the force? That's m2g. What's the angle between the force and the distance? So let me show this here. That's your distance r. That's your m2g. Am I out? Oops. I think I should move the. Oh, I think this. Yeah. Luckily, the figure is also there. So this is your distance r. That's your m2g. And that's 90 degrees. Angle between them to project the line outward and whatever is the angle between them, that's 90 degrees. X we want to solve. M2 is 80 times 9.8. And sine of 90 is 1. That's 1. So we have 80 times 9.8. Let me get the numbers. So that's 784. So that's 780 x. That's an unknown there. Finally, I can do torque due to the mass m also. This one being on the right side of the axis, it is clear that it is pointing down, so it will go clockwise. So that's negative. So that's negative capital. How far is it? That's d, right? So that's small d times mg times sine of 90 again, because this is again perpendicular to the distance in there. So that's d is given for us to be 0.10. M we said is 10 kgs. That's 9.8 and 1. So 10 into 0.1 is 1. So this is 9.8. That's minus 9.8 Newton meter. Is that correct? I think so. Yeah. How did this become so weak? Because this is 0.6. Yeah, that's correct. 18 into, so that's 18 times bigger. Yeah, that's correct. Okay. So that's your three forces that we calculated, and all this has to be equal to 0 if there is no rotation to happen. The total torque is equal to tau 1 plus tau 2 plus tau from the Planck plus the tau torque from the normal force. All this has to be 0. If it is not 0, this will move exactly like the force equal to ma. There will be a linear acceleration if the force was not zero. If the torque is not zero, there will be an angular acceleration. But we don't want that, so this has to be equal to zero if we want to balance this. So put this all together. So we have 0 is equal to minus 180 Newton meter plus 2 is 780x. M is minus 9.8 plus 0. That's what it is. So 780 times x is equal to 180 plus 9.8. So x would be equal to, that's about 190. So that's 190 divided by 780. And this will be in meters. So that's 0.24 meters, which is 24 centimeters. All right. So after, if this was a 1 meter long plank, after 10 meters, there are about 40 centimeters left here. So we are about 25 centimeters from the axis. And one could have, like, intuitively, this is very clear. We always use this. So hopefully this is very, it shouldn't be hard to digest that. Let's also do one more example, very closely related, so that this equilibrium concept is clear. This is called a static equilibrium. We are actually balancing quantities here. Notice that we did not have to use the Newton's law here. Actually, that is valid. The normal force in this case, the normal force actually is equal to m1g plus m2g plus capital Mg. So if we are interested in the normal force, that's the equation you would use. We didn't have to use that in this case. So let's do another example where this comes out more explicitly. Go to the first code. So this is an example involving a bridge. Okay, so there is again a plank resting on two poles or two pillars, let us say, which is on the very edge. Right? That's a pillar. Right? This is another pillar. So this is a plank that is resting on there. This is ground in here, but I'm not drawing it so that there's less clutter in there. Again, this is let's say this is a uniform mass. So the center of mass is right at the center. Its weight will be mg acting downwards. But now, if that's your plank, then there is a normal force that acts on this side and on the other side. There are two places of contact. There are two normal forces that act. Let us say this is a pointed object so that the normal force is completely acting at one particular point. And we would like to know what is the normal force N1 and N2. But if this is completely uniform and equally distributed, we know that they will be divided by 2, right? So let's actually change the equilibrium point by, let us say someone is standing on this plank, and let's say that's mg. So capital M is the weight of the plank itself, and small m is the weight of someone who is standing here. So imagine someone is standing or holding onto this, hanging onto this, or standing on that. One can imagine that this is a bridge, either way. And we would like to know what is N1 and N2? Like this time, this won't be equally distributed, right? There is more weight onto the right hand side, so there will be more force on the right hand side. Okay, so our goal is to find out what these are. So let's say this is 1 meter. So that's 50 centimeters, and let us say this is again 10 centimeters or 20 centimeters. So that's 0.20. So this could be D, and that's your L. L is equal to 1 meter, and D is equal to 0.20 meters. That's 20 centimeters. Let's put our M to be equal to 50 kgs. And capital M could be, let's say, 20 kgs. Like all two significant digits. And our goal is to find out what are the forces acting on the two pillars. So that is, what is N1 and N2. Find N1 and N2. We immediately know one equation that all these forces has to balance. So we have N1 plus M2 is equal to Mg plus capital Mg, which we know is equal to 50 plus 20, 70, 70 into 9.8. So that's 50 plus 20 times 9.8. So that's 686, and since it is two significant digits, so that's 690 newtons. So that's one equation, immediate one. But now we can also do the torque, right? So we have to choose an axis. Notice it's not very obvious here which is the axis. Where does this rotate about? In those situations, you can pick any point as an axis. So let's pick this to be your axis. So the center. You can pick any point. If there is any confusion, give preference to the center of mass. Center of mass is always a nice point to pick, if at all there is a confusion. Often when things start moving, that becomes relevant. And in that case, pick center of mass as your axis. That helps. So if that's the axis, then we have to again say torque due to normal force 1 plus torque due to normal force 2 plus the torque due to capital M plus the torque due to small m has to all equal to 0. Why 0? Because this is not moving, right? If this is moving, then there is an angular acceleration. We are saying this is not moving. Move the camera. What is 1? 1 is N1 times the distance from here, which is L over 2. So notice this is going to go this way, right? That's clockwise. So that's minus. I'm doing, since it is 90 degrees, it is going to be 1. So I'm immediately writing that it is N1 times the distance, which is L over 2. That's a force, that's a distance, sine of 90, that's equal to 1. Torque 2 is going to go clockwise, so that's positive. So that's N1 again, sorry, N2 again this time. L by 2, because it's half the length from the axis. Again, it is 90 degrees, so that's 1. So distance, force, and sine of 90, that's 1. That's torque 2. Torque due to the mass of the plank, that's at the position of the axis itself, so that's 0. The distance from the axis is 0 for this. This is not going to cause any rotation. And what about the mass of the person who is standing on this? That's going to tend to move it clockwise, right? It's going to move this way. So clockwise is minus, it is mg times how far is it? So that's distance d. And again, it is 90 degrees. So that all this has to equal to 0. Move this around. So we have minus n1. So I'm going to divide by L over 2 all through. So that's plus n2 is equal to mg times, when I divide by L over 2, so that becomes 2 times d over L. I did a few algebra steps there. I divided by L over 2 each term. L over 2 in the denominator makes the 2 go to the numerator. So there are 2 equations I get. I have to solve them. This is my Newton's law, gave me this equation. So that's this. So Newton's law gave me the equation that n1 plus n2 is equal to 690. And the torque gave me the equation n1 plus minus n1 plus n2. This can be calculated, right? So put the numbers in here. So this is equal to m was 50, 9.8 times 2 times distance d, 0.20, and L was 1 meter. So that's equal to that's 196. 196 Newton meter, but actually it is Newton because I divided that out by the distance. That's newtons. That's 196. Once I have 2 equations, I can solve for them. I can simply add them, right? That gives me my n2. So this is 0. So that's 0 plus 2 times n2 is equal to, that's 700. 896, that's 886. Right, so n2 is equal to 443 newtons, which is the same as 440, right? 2 significant digits, that's 440 newtons. Once I have my n2, I can calculate n1 by substituting it back in there. And 1 plus 440 is equal to 690. So n1 will be equal to, subtract 40 plus, so that's 650, and that's 250. Right? So 250 newtons. That's 690. Yeah, if you add them, that comes out 690. So there is more force, more pressure acting on the second pillar because you're more towards that. Again, intuitively very clear. But now we want to, in the next step, we want to make it move. These are all static situations, relatively intuitive, but now we want to make it move by actually releasing one of the pillars or doing stuff like that. But before that, we have to introduce what is the inertia associated with these motions. It's very clear that distance plays a role. From the axis, distance from the axis is important. So how much is that role? Is it linear? Is it square of that? And what we are going to see is that it is actually related to the square of the distance from the center. That's how inertia depends for a rotational motion. And we will do that next time. It will be called moment of inertia and do rotational dynamics. For now, I'll stop here. Thanks.